breakfast of fried eggs and donuts have to do with astronomy? The answer, it can make a delicious model of an AGN. What exactly are AGN? AGN stands for Active Galactic Nuclei, and as the name suggests, they are found at the heart of some galaxies. AGN are really bright, sometimes even as bright or brighter than the sum of all of the stars in their host galaxy.
In the unified model of AGN actually look quite similar to a fried egg surrounded by a donut. There's a central black hole, the egg yolk, surrounded by a rotating accretion disk composed of mostly hydrogen gas, the egg white. This is all surrounded by a thick, dusty torus, the donut.
Why is it important to study AGN? Well, there are many reasons, and here are just a few. First, the supermassive black holes that they contain could be the cause and catalyst of galaxy formation. Moreover, quasars, one of the main types of AGN, are some of the most distant observable objects in the universe. By studying them, we could get a better understanding of how fast the universe is expanding. Finally, AGN are some of the most continuously luminous objects in the universe. So, if we want to observe to the edge of the observable universe, AGNs are a vital tool. However, there's one major problem. We don't know how far away AGNs are, which is an important piece of information in answering the previous questions. To find this distance, we actually have to find the size of the accretion disk, because once we have the size of the accretion disk, we can get a better determination of the size of its emitting region, which means we could get a better model of its luminosity. Once we have its luminosity, we can find the distance by using the equation brightness equals luminosity over 4 pi distance squared, where distance is the distance to Earth. So now the question becomes, how do we find the size of the accretion disk? Well, the answer is through continuum reverberation mapping, or CRM. We can't directly see the size of an AGN, but through continuum reverberation mapping, we can determine its size. CRM uses the different wavelengths data over the same time domain.
For reasons not entirely understood, there is an increase of energy in the accretion disk, of which some appears to originate directly above the black hole in something called the lamppost event. This energy radiates outward and is first absorbed in the inner portions of the accretion disk, and since it is hotter, it re-radiates out in the ultraviolet spectrum. This energy continues outward, so as more time passes, it reaches further out in the accretion disk, where due to the cooler temperature, the energy is re-radiated in the visible spectrum. The energy continues outward even further, and as more time passes, it reaches the inner edge of the dusty torus, where the temperature is even cooler and the energy is re-radiated in the near infrared.
As the energy emitted by this unknown phenomena varies, the time delay from the same variations at the ultraviolet to the infrared can be used to determine the distance using the simple equation distance equals speed times time, where speed is the speed of light. Once there are enough CRM studies, we will get a better understanding of the size and structure of accretion disks. Then we will be able to get a better determination of their luminosity. This all means that our understanding of the universe will get a little bit brighter. And now, I think it's time for breakfast.